So welcome everyone. Welcome to this session of sequence alignment, the next second segment of the sequence alignment. So taking the information from the last lecture that we had discussed thoroughly, that what are the basic concepts of sequence alignment, what are the different attributes that we had talked about. So like the past lecture, this lecture will be focused on providing a complete understanding under a specialized head, and that specialized head is pair-wise alignment. In that pairwise alignment, we will be talking about two major algorithms, Needleman and Wunsch, that is used for global alignment, and Smith and Waterman, that is used for local alignment. Now what is global, what is local, that we had already established the basic understanding. So with that outline, let us begin, and the things that we had discussed last time, that these are summarized here just to recapitulate your memory, that where we left yesterday and then where we have to begin from now. So we were discussing regarding the substitution matrices. We were talking about the substitution matrices, where we wanted to understand that how the scoring is done. So we had discussed the dot matrix, we had discussed the unitary matrix completely, and now we should focus on the next segment that we wanted to talk about in dynamic programming algorithm, and that process is substitution matrix. How the numbering is happening. When I told you that yes, the presence of what you say, the addition or the incorporation of any amino acid in terms of alignment depends upon the neighboring or the adjoining amino acid, and that is called as propensity value, or whether the same amino acid can be aligned or not. So, all taking all these parameters into consideration, people designed two basic matrices called as substitution matrices. Now, what these matrices are all about? These matrices will define you that if you are combining two sequences, if you are aligning two sequences, how much homology is there? It will give you a definite scope. It will give you a definite scope. Then, apart from it, next is what information you're getting. You will be getting a very sound information in from this scenario. You will be getting a very sound information in this scenario. Just give me a moment. You will be getting a very sound information in this particular aspect. What that information is, the information regarding what is the exact score that we are talking about. Like if I have, let's talk about, I have 10 different sequences that are aligning, which one is much better? Depending upon the score, high score, you can pick which one is far better than the other one. Then we have you can also see that what is the distant related sequence. If you're talking about evolution, what is the distance related sequence that we're talking about? So there are two type of basic matrices that are still used in multiple tools. First is pan, point accepted mutation, and another one is blossom. Now different variants are available for blossom. That's why I've written X here. What this X means, it means that X means the similarity percentage. If I have a query, I am matching it with the database sequence, how much percentage similarity is I am keeping as threshold, whether I'm talking about 60%, so I'll be calling it as blossom 60. If I'm calling it as 80%, I'll be calling it as blossom 80. So based on that, these particular matrices were designed. Then the method that they use, the method for local alignment that is used. I'm not talking about the complete global alignment. I'm talking about the local alignment of these regions, these boxes that I'm making. You have to clearly narrate that what is the length of these boxes. Now, in case of nucleotides, the length varies from 6 to 8 nucleotides, 6 to 9 nucleotides. Whereas in case of amino acids, this box size is reduced to 1 to 2 amino acids. And in certain tools, this size also reduces to 3 to 6 nucleotides. 3 to 6 nucleotides. So what you have done, you have fixed the 6th position of nucleotides, and then you are matching it with the complete database sequence. And then you are saying that if the threshold is there, if I found the alignment of these sequences, then only I'll go for the alignment of the remaining portion that is there in the sequence, that is there in the sequence. And this approach that of aligning first the very small segment pairs, or the word that is called as k-tuple method. The boxes, these boxes are actually called as k-tuple. Now, the k-tuple value you have to define that if you are using DNA, the k-tuple value may range from 3 to 6. If you are using amino acids or proteins, then this k-tuple value may range from 1 to 2. And if you are using this method of first aligning the local region of words and then extending in both the direction, if the threshold is there, that approach is called as heuristic approach or heuristic method of alignment. So when you will be going through the bioinformatic course in your curriculum, you will be continuously understanding or reading this particular word, heuristic approach, heuristic method. But nobody will tell you what exactly is that particular method unless you enter into the alignment zone. So please remember that this particular method is nothing but it's first the matching of these k-tuples and then extending the aligned sequences in both the direction to have a significant alignment. What is why we are doing this? Why we are doing this particular step? See, I have 1,000 nucleotide sequence, very short sequence, 1,000 nucleotide. I started joining one by one. It took me 10 hours. Why? Because this query will be aligning with all the database sequences that are present one by one. Whereas if I use these short methods, then these two amino acids only will be first aligning with all the sequences. Out of 1 lakh, they will be filtering out, say, 50 sequences for me. And then these 50 sequences will be going for complete alignment. Whereas earlier, I was aligning all the complete 1 lakh sequences. So the time taken in global alignment is way higher compared to local alignment. That's why it's a fastidious process. And the tools that we use are BLAST, basic local alignment search tool, and fast alignment. That's why the name came, fast alignment actually. So the matrices that I'm talking about are percent accepted mutations or the point accepted mutations, or you are talking about the BLOSSOM, which says blocks amino acid substitution matrix. That's why the name came BLOSSOM. Now this is how the matrices look like. This is how the matrices look like. This is PAM, this is your PAM, and this is your BLOSSOM. This is your BLOSSOM. Now let us see majorly what was the difference. Now see BLOSSOM, if you're talking about BLOSSOM is based on local alignment. Whenever we'll be talking about local alignment if you're talking about BLOSSOM. So the BLAST tool that you use is working on this particular matrix called as BLOSSOM matrix. Now it was introduced by Heinikov, both the Heinikofs and also by Altschul in 1994. Now what they did, they scanned the similar regions of all the conserved domains in the protein families, and then they assigned the values. They assigned the values to all the 20 amino acids and formed a matrix. How they assigned the values? They assigned the values that the values on the diagonal represents the favorable event that if the amino acid has to come. Suppose a tryptophan W is to come, then the value from BLOSSOM matrix will be 11. I'll be writing 11 as the matrix. Now, if the substitution happens from W, the amino acid is changed to valine, then you see the W and valine value is ranging here. W and valine value is ranging here. That is -3. That will be the penalty that I'll be focusing on. So that is how what they did. They counted the relative frequencies of the amino acids, all the frequencies of the amino acid, that if W is present, what should be the frequency of valine that I should be talking about. And also they took into account the probabilities of substitution. What are the probabilities of substitution? What are the likelihood of substitution, fine, among all the 20 amino acids? And then they designed this particular matrix. Now please remember, these scores First, they calculated the probability values. Then they converted those probability values into log odd scores, log scores. Now these values, what you see, are log values, log score values, and they did this for all the 210 possible substitutions that arises from 20 amino acids, that arises from 20 amino acid, and you can do it by 20C2, the combination part that you'll be getting. Okay, then let's talk about PAM. Let's talk about PAM. What PAM did? What PAM did, PAM actually grouped the complete amino acids based on their side chain. I told you the amino acids grouping in the form when we were reading the single letter form. So what they did, they clearly quoted that cysteine is sulfonyl, they kept it as separate group. The STPAG, serine, threonine, proline, arginine, and glycine, they called as small hydrophilic, and so on. They group like wife, they grouped it for aromatic, and so on. What they did, they give plus 10 score. They give plus 10 score if the mean the plus 10 score will be meaning that the ancestor. If you're talking about the divergence part, then the ancestor probability is data. I'll tell you what that does mean. Then if the value is 0, that means the probability of that amino acid present to be present on that position are equal. A probability or a score of -4 means that the change is random, that the change is happening at random. So if you are calculating the probability of aligning these two sequences, I want to align. Then if you see the score, y is 10. Y aligning with y is 10. So I'll be writing 10 plus 10, 20. Whereas if I am looking for aligning YY with threonine and proline, again you see there is no match, there is mismatch. So what score I'll be putting for a mismatch? I'll be seeing Y, I'll be seeing T, and I know that the score is -3. I'll be seeing Y, I'll be seeing P, and I know the score is -5. So cumulatively it is coming at -8. Now what -8 is showing you? What -8 is showing you? -8 is showing that it is highly unlikely. It is a very rare and unexpected event that has happened between these two homologous sequences, because cumulatively the score has come to -8. -8 means highly unlikely. And similarly, plus means that the probability of this particular event happening is very high. The probability of this particular event happening is very high. And that is how we calculate the substitution part. That is how we calculate the substitution part. So let us see with an example. Okay, so I have a sequence here, it's clear, and I have a sequence here. I'm matching these two, and there is a single gap that we have incorporated. When we are matching V with V, let's see V with V, that is valine with valine. Valine with valine will be giving you a score of 4. Fine, valine and valine will be giving you the score of 4. That's why you're getting the score of 4. Okay, so similarly you can match, and the score is written here. Okay, so the score is written here, and with the gap, the L, with the gap of L, that is leucine, the gap of L, we have incorporated the value of -11. We have incorporated the value of -11. So the total score, once you sum it, will be coming to 26 minus 11, that is 15. Now what this is showing? What this is showing? It is showing that these sequences, first of all, are non-identical because the scoring has reduced. Fine, there is a certain place where there are substitutions, there are certain places where there are gaps. Then the score which you have obtained by every match is not the same. It is different. Why? Because the probability of substitution is also dependent upon the neighboring amino acids. Also dependent upon the neighboring amino acids. And for example, if you are talking about two rare amino acids, there will be score that are more than 2 times common. That is rare, right? And then when we are talking about aligning the gaps, then we have incorporated the penalty of the gaps. So let us see in much more simpler form of dynamic programming. Simpler form of dynamic programming. Let's talk about the alignment part. Suppose we are aligning a query with the database. We started from first position. Right now, we have reached to sixth position. We are standing on sixth position. Okay. So previous score till fifth position is here. I started with matching BB, DE, SS, and there was a gap. So the I got a score of 8. Now next is by and by. It's perfect match, so I should write 7, and the total score of the 6 aligned amino acids will be 50. Fine. So what it does, it carry forwards the aligned score and keeps on adding at every fresh place. That is called as dynamic process. You are keeping a memory of what has happened in the past, and at this position you are adding, then you are taking the memory, going ahead, taking the memory and going ahead. That is called as dynamic programming. And if the score is -1, that also is taken forward, and then again the net score is obtained. And this is how we move from 6 to 7, 7 to 8, 8 to 9, 9 to 10, and so on. The complete alignment scoring is done until the alignment is reached to the end, until the alignment is reached. So for the based on these scoring matrices, the algorithms which were designed were two algorithms. For global, we will be talking about Needleman and Wunsch. For local, we'll be talking about Smith and Waterman. We'll be talking about Smith and Waterman. So we'll be talking about it in very brief. Although you people must be familiar with this particular scenario, with this particular table, once you have gone through the genomics, proteomics, and the bioinformatics courses. So let's talk in our manner. Then we'll be talking about the text, what we're trying to give you, and we'll be taking a very short example of the sequence. We will not be going in that detail. So let's talk about this particular part. Let's take a sequence of A, D, L, R, S, T. Let's start the very short sequence. I'm matching this with A, R, R, S, T. So I have a query. This is my query. I want to align it with my data, with my another sequence, that is this particular database sequence. Fine. So this is my one pair. So I'm going for pairwise alignment. This is my second pair. Okay. So how the complete sequence will be aligning from here to here, and in terms of global scenario, we are discussing Needleman and Wunsch. So first of all, a matrix will be formed. First of all, a matrix will be formed. In this matrix, the computer will be aligning the complete data, the complete sequence that you want to align in this manner: A, D, L, R, S, T, and also here A, R, the database sequence that you want to align, R, S, T. Then you can prepare the rows here. The complete grid can be prepared, although you have to prepare, but the module in the computer is already done that. Once you have entered the sequence, once you have entered the complete sequence, the module is already ready to perform, and it performs in fraction of seconds. So the basic rule, that we should remember is match, the score is 1, mismatch, the score is 0, and penalty, I have also written here, gap penalty or the mismatch, we are going the score of -1. So we are not talking about the -1 mismatch, we will be talking about gap penalty. If I am inducing gap, I'll be giving a penalty of -1. So let us see how it goes. What you have to do, you have to move row wise, and you have to write wherever the score is there. So first of all, do nothing, go for match and mismatch. I am writing 1 because match is there. Mismatch 0, 0, 0. There is no match. For R, 0, 0, 0. I have a match here, 0, 0. Like the way I did for unitary matrix. So what you did, you completely filled this particular matrix with the score. Let me fill the matrix with the score, and then perhaps we will show you how that thing is going for backtracking, how that thing is going for backtracking. So once you are through with your unitary matrix part, now this is the first stage what an algorithm is performing at very preliminary or basic stage. Then next is what? Next is the analysis part. Next is the analysis part which this particular matrix will perform. Now it will always start from the last unit cell of the matrix. In the global alignment, when you are trying to decipher the common regions, the similarity regions, the computer algorithm will always start from the right hand lower corner of the unit cell, and then it will move diagonal. So what is the thumb rule, or what is the trick of moving diagonal? If you are moving diagonally, you will be carrying the score which is present in this particular cell. I'm calling it is I. This cell is called as J. So what I'm doing, I'm carrying a score of 1 to J from I. From I am carrying a score of 1. So now 1 of J, 1 of J plus 1 of I. Cumulatively, now the score in this position is turned to 2. Now the score has turned to 2. Fine. That is cleared by this time. Then the score that I carry forward, I will be going on ahead in both the directions. So you see what is happening. I am bringing the score from the unit cell to the new cell diagonally, and the carry forward score always, please remember, the carry forward score always moves ahead. The carry forward score will move in upper direction and will also move in horizontal direction. So now the new score of this will be 1, 1, 1, and here also it will be 1, 1, 1, and 1. Fine. That is thing. Then you again move diagonally. Now you are bringing 2 along with you because the score of this cell is 2. So 2 plus 1 in this cell is again 3. 2 plus 1 in this cell is again 3. Now the carry forward score is 2, and always the carry forward score will be moving ahead and horizontal. So the direction, in this direction, you will be having a 2, 2, 2. And if you move ahead, then again 1 is there. So you need not to worry. You just add 2 plus 1, that is 3, and go ahead again 2. Why? Because carry forward score is 2. That will be your new matrix. And then again you move ahead. Now it is 0. It is 0. So 3 plus 0 is again 3. And you are bringing 3. So you will be writing 3 again, then 3 again, and here also 3. And this is how you will keep moving. You will keep moving, and you will be getting a score of 3 also here. You will be getting a score of 3 here also. Now this 2 will move. This 2 will also, this 3, so this 3 will move in this direction to give rise to 4. To give rise to 4. So this is how the last final appearance of your what you say matrix will be looking like in this particular fashion. In this particular fashion. So when I will start analyzing after finishing it, when the computer starts analyzing that where is the similarity region, now what it will do. Please observe carefully what it will do. Let me take the black color. Yeah, what it will do. It will first stand here, and it will start backtracking. It will start backtracking. See where, till what point the score is increasing. Till what point the scoring is increasing. If you observe diagonally, 1, 2, 3 is increasing, and after 3 again we encountered 3. So the backtracking will halt here, and it will say that a short segment of RST is the region which is actually having the similarity. Then it will see again from where the score is increasing. It will recognize that from here there is an increment in the score. So it will see that now the similarity region is here. The similarity region is here. The ARST. But there is another crucial thing. What crucial thing I'm talking about? Please see carefully. The 3 which appeared here, now the computer will see if I go ahead, I should not encounter, any increment in that particular region. Now it immediately sees another 3. And this is how it will determine that if this region is common to this, and there is an increase in the scope when we are moving from this channel to upper channel, then the alignment should be ADL R ST along with A, R, R, ST, and in between there will be a gap. In between there will be a single gap. Fine. So the scoring, final scoring, this is the alignment. Now the final scoring will be coming in this manner. You have 4 matches, so plus 4. You have one mismatch. So if I am counting, suppose for scoring I am getting more stringent, and for one mismatch I am giving penalty of -1, and for one gap I am giving a penalty of -1. So the net score will be +2. And if I'm using mismatch as 0, so the net score will be +3. And this is how different tools based on Needleman and Bush algorithm are performing this particular alignment. And that is in nutshell what we have discussed in this particular slide, that you have to go ahead and label it. Now, if I go for +1, -1, so you go horizontally, you keep going horizontally, and you will first label it completely, and then you start backtracking diagonally. And the way we have labeled, you start labeling, and you will end up in this particular format. And this is perhaps the simplest form that we can understand that particular alignment. Advanced stages, it gets again in different variables. So first of all, you should get a guess of this particular scenario, that what is happening. Now, when we talk about the real-time part of these matrices, then in the real time, the values are already assigned. The values are already assigned with a basic dummy variable, where we are giving a dummy variable. The first row and the first column of the matrix, the first row and the first column of the matrix are always filled in the algorithms that we are using these days. Now, let me show you. This is the first column that I'm talking about. This is the second column that I'm talking about. These are always filled as depending on the correction factor. We are filling it previously. Now, we had already understood the backtracking method, how the backtracking is there. So every score, the computer, we had started from this particular unit and we moved in diagonal direction, keeping in mind that the carry forward score is moving in both the direction. And that is how the computer algorithm does the things for every single score, and repopulates the complete alignment, and then it gives you a final track, which is the most common pathway that you will come across. The final track, which is the most common pathway that you should be focusing on, So this is how the complete global alignment is done. Next was local alignment. They took the information from global only, and based on that information, they redefined it in terms of local alignment. So the people who were responsible for this were Smith and Waterman, and still this algorithm is used in multiple tools. So what they did, they aligned the two sequences based on the algorithms what they designed, and let us see that without wasting much of the time what they did. See, they were very clear in the notion. They were very clear in the notion that the dissimilarities or the differences are arising because there will be many mismatches and gaps that will be present in case of any aligned sequence. So what is happening? What they are doing? They went for the same type of arrangement. Let us talk about the same sequence that we have shown: A, D, R, S, T, K. Let's talk about this, and we have matched it with A, A, L, S, T, K. So if you want to match these two sequences, what they did, they first incorporated a dummy variable. Again, a dummy was there, keeping XX and XX here. So they labeled it at 0, 0, 0, 0, and they provide the initial score of dummy. This is not an alignment. This is a dummy aligned row or dummy column that we are talking about. Dummy row or dummy column. So this dummy row and dummy column is here. Now the actual alignment will start once you go ahead in a similar manner that we talked about the Needleman and Wunsch, in the similar manner. So how it is going? They started with the match score as +1. Fine. A match score is +1. A mismatch is 0. a mismatch is zero only in one condition. Only in one condition. Actually, they give the mismatch a penalty of 0.33. They give the mismatch a penalty of 0.33, keeping in mind very clear view that the matrix will never accommodate a negative score. So wherever a negative score is coming, I will change the score back to zero. I will change the score back to zero. So how they align? Let me again just wait a second. Let me put it in a clear manner. T K. Let us align. Now here is dummy part, and then A L S T K. So how they started populating? Let us talk about this. Is 0.0. This is again 0.0. Now 0.0. You will see there is a decimal that I am putting in every place, and this is how it was repopulated into the directions. Now let's see. Match 1. Mismatch minus 0.33, but minus I cannot put, so I'm writing 0.0. Again 0.0. 0.0. Okay, so let's see. L mismatch again 0.0. Fine. Now this is a crucial cell now for me. LD, yes, the penalty is minus 0.33. Now in Needleman and Wunsch, once we prepared an algorithm and then we are moving from the left right hand corner to the diagonal direction. In this, everything is happening simultaneously from this unit cell. From this unit cell, we are moving diagonally, or every score will move diagonally. Now, since I have 1 as a score in a diagonal position, it will move forward. It will be carry forward. The carry forward score is 1. The carry forward score is 1. The actual score based on L and D match is minus 0.33. So the new score will be 0.67. 0.67. So I'll be writing round off. Let's round off 0.67 to 0.7. This will be my new score. This will be my new score. Then I move ahead. Again a mismatch. Minus 0.33 minus I cannot write, so 0.0. Suppose if 1 was present here. Suppose if 1 is present here. The moment I will go here, again there is a mismatch. 1 will be carried forward, so the new score will be 0.77. Now let us see. 0.0, no match. 0.0, I came to this cell. Now 0.7 is carried forward. 0.7 is carried forward. Then again a penalty is there. 0.33. So 0.77. Now there is, because R is not matching with S, so there is a penalty. There is a penalty of what, say 0.33. So 0.33 is there. So I'll be getting what? I'll be getting 0.37. Let's round it off to 0.3. So I'm writing here 0.3. Okay. Then I went ahead. Now I have a match. I'm writing 1, then 0, then 0. Then I moved in this direction. 0, 0.0, 0.0. I came here. Now this is carried forward as 0.3, and there is a penalty of minus 0.33. So the effective answer will be 0.0. Then I moved here. Now I have a diagonal 1. This is carried forward in diagonal position. And now my new score in this particular section, will be 1 carry forward, T match with T. So 1 will be the matching score. So 1 plus 1 will be my 2. So I'll be having 2. And similarly, I'll be having a 3 here. So what now? What your algorithm will see? Once the complete metric is done, it will track where is the continuity increase in the score. It is 1, 2, 3, and then there is a 1. So there are 2 regions in the sequence which are sharing homology, STK and A. And this is how fast process is there. It is not making double algorithms and then going for backtracking. No, simultaneously the scoring system is being given, and simultaneously based on the previous score, everything is being channelized. And this is what happens in case of your Smith and Waterman alignment. And this is the real-time data that it provides you in no time. This is actually the real-time data, how we will see when we are performing the blast sequences. So that is what that it's a very high scoring local alignment part that has been designed based on Smith and Waterman, and the basic thing that how this thing is done that I showed you, that is represented in this text format in the slides, that what scoring should be given, what scoring should I be giving, and how we will move forward. Don't, if you are not understanding what how this algorithm is moving, just remember what I told you and how this thing is done. This is perhaps the simplest explanation that we'll be getting of the Smith and Waterman algorithms. Now once the tracking is done, it will give you an alignment, final alignment, and then the score will be there. So that is the thing that I wanted to tell you in terms of alignment. So right now what we have done, we have understood in brief the theoretical aspects of the complete alignment part, and our next job is to perform the alignment. Now, in performance, we'll be focusing on two softwares, first of all, for local alignment, and that is BLAST, that is regularly used, and then fast alignment, that is regularly used. And then we'll be going from pair-wise alignment to multiple alignment, and we'll be using different softwares to decipher multiple alignment. And that will be the in nutshell, thus then conclude the session of alignments. Fine. So thank you so much. We'll stop here and we'll again meet in the next series of lecture uh, with the future topics of bioinformatics. Till then, please take care and wish you a happy learning.